Joe asked me to do this presentation is to come here looking for or searching for collaboration. So I'm not expert in machine learning. We do apply it, like you said at the presentation. So all what I will present is what we do for machine learning as application. We are not developing any sort of soft skills or any sort of algorithmic aspect of machine learning. I know most of you are experts, and please forgive me if I do some mistakes in my presentation, especially with machine learning or artificial intelligence. Okay, so this is a work we started to do 2 years ago. So I'm working on this university where main research we do is with OCP. So all the research we do there is connected to phosphate and its derivatives. So what I will present today is some application of machine learning on how can we solve the challenges for transporting phosphate from Polytechnic to Durham. So that's something I will show you. And other thing which I add to this title is I will show you also some work we do at Durham University using machine learning to do sediment transport. And they will show you a couple of case studies where machine learning really can solve a lot of problems. Nowadays, this is what we call a fashion. Everybody is championing the boards and trying to use machine learning to solve these sort of problems. I need to thank my collaborators, my colleague, is here, and these are two PhD students that are currently working on this topic. So, forgive me first, I just show you a video where, before starting my talk, and hopefully
to further consolidate its leadership position in the global phosphate market, OCP Group innovates by introducing the slurry pipeline, a new mode for the transportation of the phosphate pulp, both competitive and environmentally responsible. With an investment of 4.5 billion dirhams, this new process increases the transportation capacity to 38 million tons per year, from the mines to the joyful asphalt platform. The logistical costs are approximately reduced by 90%. Covering a distance of 235 kilometers, the slurry pipeline revolutionizes the entire value chain of the group's industrial activities, ensuring total integration of upstream and downstream operations. Raw phosphates originating from the Khoribga mines are then enriched in the washing plants. The phosphate pulp is first stored in tanks and then pumped via secondary pipelines up to a collecting station called head station. Then, the ore is sent through the main pipeline to the terminal station, located inside the Jorfel Asphalt platform. The station has 8 pulp storage tanks of a total capacity of more than 50,000 cubic meters, as well as a control room. The construction of the pipeline has mobilized more than 50 subcontractors and required the use of close to 800 machines. It has also generated 250 permanent jobs and no less than 1.7 million man-days throughout the entire construction phase. A genuine technological and technical feat, the crossing operations made it possible to lay the slurry pipeline under 65 roads, the SETTAT Marrakesh Highway, the railway tracks, and even the Rabia River. The slurry pipeline also addresses the challenge of ecology. The elimination of phosphate pulp drying at the mine level enables a significant reduction of CO2 emissions by more than 930,000 tons per year. Furthermore, the pipeline helps saving more than 3 million cubic meters of water each year. Thanks to this first slurry pipeline, OCP Group further consolidates its status as a socially responsible world leader.
Okay, so that's just to show you what we mean by slurry pipeline. So usually in the past, this is the mines where we get the phosphate. So to transport the phosphate from Polytechnic to local asphalt usually was by train. So it's very expensive and also it's not for optimizing the production. So what they did, so they built a pipe. This is a pipe which is 187 kilometers, and those are the mines, so near there, and also the Mrah. These the two main mines where we get phosphate. So they grind the phosphate, they wash it, they mash it, they put it in the tanks, and then they pump it in the pipe to go to the platforms where they process to get the fertilizers. Okay, so our work, or what we are trying to do, is to try to understand how the slurry pipeline works and how can we optimize the production, which is still a big challenge. This is one of the best, or if you want, one of the challenging projects in Morocco. So that's optimize the production and also speed up the transport of the phosphate from the head station to the terminal station. So now what we do, we blend the phosphate, we mix it with water. Up to now, the capacity of the pipe, we are using only 60% of phosphate and 40% of water. And all the water we are using here is coming from Morocco. So we are wasting a lot of it, if you call it wasting. We are using a lot of water to transport the phosphate. So it's true, we have solved the problem, but still there is another drawback, so there is a challenge. So we want to optimize the production, we want to optimize the phosphate. What do we mean by optimizing? So instead of having 60% of phosphate, 40% of water, we want to put here 80%. That's the target. 1%, if we are able to increase the production with 1% of phosphate in the pipe, is Mehdia of Durham. So it's really a lot of money. So then, what we do, we have people working on the slurry pipelines, they're trying to optimize this production. So we want to understand first what is going on the pipe, how can we increase the density of the phosphate inside the pipe, how can we understand also the hydraulics and also the rheology. Okay, the biggest challenge we have now in Moroccan phosphate, we don't know exactly the constitutive rheology, and that's where we are working. For some mathematicians, we can apply mathematics. We are trying to simulate, to model, and then use the tools for machine learning, because possibly has a new set of data. We have data from 2012 until now. It's a very, very vast set of data. Anything you want, we have in this pipe. So they have an optic wire along the pipe. We can monitor the pressure, density, anything we want. So that data we want to make use of. So that's the target. And now, if we are going to model this, why not using this data to feed up our model? So that's exactly what we are doing. So we are not doing it only modeling using PDEs or numerical methods, but also we are using some data and machine learning tools to fit this, like if you want variation or average approach. Okay, if you have done PDEs, that's the sort of equation we are solving. I put it very simple to understand what's going on. So that is never stop equation. You have incompressibility, because the water is incompressible. You have density, and then you have a term of the transport, and then you have a pressure, and then you have the stress or the shear rate. Okay, that's standard. You can find it in book. Anybody done mobilization before, you would understand what these terms are. Okay, I make it simple, but it could be very, very complicated, because you have two phases in the pipe. So we're talking in the pipe. You have water, you have slurry, and you have the particles, they are jumping up and down and transported in the pipe. So we want to make the thing very simple. So if you have a fluid in the pipe, these are governing equations. Now, where is the problem? The problem is in this tensor, you see that? Because that tensor gives you the relation between the shear rate and the surface stress. And that depends on the type of fluid you are dealing with. If you look at the next slide, so if you are dealing with Newtonian fluids, that relation is linear. That gives you the viscosity of the fluid inside the pipe. However, in our case, the fluid is not Newtonian, it's a non-Newtonian, because you have shear rate, and also some elasticity there. Now, if you go for that non-Newtonian fluid, you have this relation. And then you move from a linear to a non-linear. And there where the problem starts. Up to this time, I'm talking to you, we don't know this constitutive equation. We don't have a constitutive equation for Moroccan phosphate. We have many fluids, like the honey or the toothpaste. We know this constitutive equation. And if we know this constitutive equation, we can easily solve the problem. Then we can understand exactly how the dynamics moves inside the pipes. But we don't have this constitutive equation. Now, what people also they use this. And this is a HASSAN, which has been developed a long time ago. And people, they have using it for honey or other fluids. But I will show you the result later. And this is how it looks like. Why do we need this equation? So this would give me the viscosity of the slime. That's something you don't know. These people in chemistry, they work on it. The material sciences, they work on it. And some of them, they even understand it as a polymer. They start to do some stuff there. But again, that's the challenging question. We don't know two things. We don't know the elasticity for the slime, for our phosphate, and we don't know the viscosity. And there we are putting a lot of money to understand these two. Because we know if we have a formula for these two, we can solve anything because we can run the simulations and then we can increase the production from 60% to maybe 70 or 75. Okay, that's what recipe uses. These are data, these are batches, because when they put the phosphate in the pipe, they send it as a batch. So they put one batch phosphate, one batch water, and then etc. So it goes like a batch. Okay. And for each of these batches, you see these are 4 batches. One batch from Polytechnic takes 24 hours to reach the terminal station. Okay. And if you see these are data, we collect it from the pipe, and these are from the head station. So you have data, so what you see those are data. And that line is the HASSAN model, this one. Okay, and this is why they believe this can be used for modeling. That is wrong, because when we go later in the simulation, you will see some deviation. You see that? So that's the real data, and that's the HASSAN model. When I say model, it's an equation, empirical equation that just related the shear rate. This is the shear rate, and this is the shear stresses, and the slope of this line is the viscosity. Just to make it very simple. It could be more complicated than this. So if I have a linear or Newtonian fluid, this will be a line, and the slope of that line will be my viscosity. That's fine, that we know how to do it. But now the problem is the phosphates start to behave more plastic to elastic, something in between, and we don't have that empirical equation. Okay, so that's what OCP exactly they are using at the current stage. They are using HASSAN, but this HASSAN is I don't think is critical. It's not the right equation to use. Now, this is where our contribution is coming. The question we ask, can we use machine learning to teach our machine based on that huge set of data? And anytime I need the viscosity, I don't need the empirical equation. I just teach my machine. Go there, do some nice tools. All guys, you know that from random forest or maybe neural networks. And then these will help me to solve this problem. I don't think we need any longer those equations. That's what we are trying to convince people to do. Okay, that's something we do. Our students, they know how to mesh the pipe to get some nice result, and then we can also simulate, if I show you, we can, that's the batch of phosphate, you can see it's just moving through the pipe. That's something we can do. But also it doesn't want this, or the client if you want. Because that's something we can do. Our students, they can solve this. This is a toy for them. They can build it. It's not a problem. The biggest problem is, can we understand the erosion? Can we get the viscosity? And then this would be just a result or a ultimate goal where we can just change the viscosity and see how can we speed the process. Can we fill the whole pipe with phosphate? That's something we are going to do. Okay. Now we move to the machine learning. So that's the data we got. So if you look at the phosphate, the component of phosphate, there's many chemical, physical parameters. It's a huge set of data we're talking about. And as you see here, so this is the correlation between all those constituents of the phosphate. And the diagonal here, it means the correlation between each parameter with each other. It's one, and then you see there's a very huge heterogeneity on that set of data. Okay. So you cannot see how these parameters are correlated to each other, okay, in terms of the physical, chemical aspect or properties of the phosphate. So we're talking about 25 parameters, and we are using only 600 samples, but we do have data larger than this set of samples. Then, if you want to understand the statistical behavior or how these parameters or dependence are distributed in the probability functions, you see there is a very strange behavior. So you cannot come up with a conclusion how your data is distributed. Is it a normal distribution? Is it a Gaussian? Is it a beta or whatever? So if you want to do a statistical analysis with this data, again, this behavior doesn't help because it tells you that you can never find a relation that tells you how your data or your density or probability density function is behaving. Because look at here, it's just one normal distribution. And then you get this normal distribution there, and so it is really a very dependent data for the slurry pipeline. Okay, so what we do, we will solve these metrics, we find the eigenvalues, because that's what usually we do. So if you have a physical problem, and inside this physical problem, you have, let's say, 10,000 parameters. You want to see which one is the dominant, which those parameters, they are really the most affected the result. So what we do, we just find the eigenvalues and then see which one. So that we get for the first one, second one, and third one. This is exactly what we got. If you go forward, remember we are talking about 25 parameters. So if you go forward, so this would be just zeros. You don't see really those eigenvalues are relevant. But you look at the first one, you see again very heterogeneous. And also that's something we talk about it later when we start to say this is a multi-scale physics. So it's not really one thing there. See the distribution there. These are the constituents. And there you see the dependence. Okay. So as I said, if you go, we are just taking 4 eigenvalues of that correlation matrix, and if you get the others, you won't see a huge dependence. But again, this is not helping because it doesn't tell us which constituent or which parameter here is the one we should consider and which one we should neglect. Okay. So that's what makes the problem very challenging. Our data access to that data, but now, if I'm going to do modeling part, I want really to understand which parameter of this is the one I need to focus my analysis, and which one I need to just ignore. Yeah. So that doesn't help. Then we need to do real machine learning to understand that. Okay, I apologize, this is something you already know. So these two algorithms we used. So we used the standard random forest. Again, we just make a decision tree and then decide we use some rule and then we come up with a solution. So you have a huge set of data. You split that data to something you validate your result and some other data for teaching your machine. So what we used in our case, we did 90% of the data for teaching the machine and 10% to validate what we got. And also we used, so that's something I will show you why we are not considering a slurry pipeline, because we do a comparison. I will show you a comparison between random forest, the neural networks, and just the linear regression, something we do all the time. And then we use the neural network because that, as I will show you, there is that non-linearity aspect in our data. And random forest won't capture that. So these would be maybe the best option to go, but you should tell me at the end whether I'm right or not. Again, so that works in a neural aspect, so you do optimize this function to find the weights. That's something we do. I don't have any extra thing to add, but for us, or for velocity, more or less, so this would be like a black box. I don't want to see what this algorithm does. I don't care. But you guys, you work on this, you need to know what's exactly there, and maybe you can find other ways to do it. Optimize, to speed up, all these things we do in the hard core. But that's a hard core, I'm not interested to see, or even the also, you input data, whatever, it cooks something here, and then gives me something to eat. So that's what I'm interested in. And each node, you see that, that's exactly what it does, and we want to find a weight for each of those parameters, and based on that, we do our decisions. Okay. But again, think about it as a black box. You input something, you get some outputs, and then you make a decision. Okay? Good. So for the evaluation, remember I said we will take 10% of the data, and then we do the evaluation to make sure we do something right. Okay? So those are the errors we use. So that's the standard errors when you do your comparison. And then, based on the errors you get, you will take into account which algorithm you will consider. So this is just the random forest, this is the neural network, the multi-layer, and then the linear regression. If you see the errors, and all these considered metrics to measure those errors, you will see that neural network, it gives more accurate results than the random forest. Obviously, the linear regression doesn't work. But this is what the engineering does. Most of the engineering have lost it. That's what they do. So they do just a linear regression and get the parameter they want. But you see, the errors are really rubbish. So all of them, they are larger than the random forest and also on the multi-layer or the neural network. What's the conclusion we see here? Remember, if you have followed me at the beginning, we are trying to quantify viscosity, elasticity for phosphate rheology. That's the key, that's what we want. And what you see here, these are the errors we get when we measure the elasticity of phosphate, how elastic this slurry, and this is the viscosity. Because if we are going to do modelization or to model the right thing, we need these two parameters. Without these two, what we do is just nonsense. Okay? So as you see, the conclusion, maybe that's, you need more investigation. So the neural network is working fine. It's giving very nice result compared to random forest and also for the linear regression. And maybe the reason why, there's two reasons. The first one is that non-linear aspect of the problem. And that non-linear aspect is not captured by the random forest. And the other thing is that high heterogeneity on the correlation metrics, because that dependence of parameter for each other also is not captured by the random forest. However, if you look at the neural network, it gives something better. Again, if you do analysis for, this one is the linear regression, that's the real viscosity, which is coming from the data, and that's what we predict. And as you see, if this data approaches the line, the diagonal lines, that means we have the real data and the predicted are exactly the same, yeah? So, but you see linear regression, you need to do something rubbish here. So it's very far from the accuracy, you see, especially for the viscosity. For elasticity, you see also some discrepancies between the real data and the predicted data. If you go for random forest, you see that data become better, so you see some data here approaching the diagonal, and also for the viscosity. But look here, that's the neural network, and it got very, well, you see some discrepancy here, but here and there you see a very good coincidence. Okay, we do the same, but this time for, that's what you see here is the linear regression. You increase the number of batches, you see also some oscillatory behavior. That's the linear regression, it captures the feature, it really follows that pattern, but it's really powerful, it doesn't turn down peaks there, you see that? Now, if you move from linear regression to random forest, you still capture that, but again, it's not fully captured, especially those peaks you see over there. Now, if you do the neural network, you see you got a very good matching over there. Okay, so that's what we have done for this case. And again, you see we can use more batches because we have data from the starting when they started production. So we have access to the whole data. So the student, our student, what he did, he just uses very simple samples, which is 600. So that can be also extended to other set of data. So the same here, if you see, that's what I showed you, that is for elasticity. Now, if you look at the viscosity, and that's exactly what we want in our model, you see that always the neural network is giving better result compared to regression, linear regression, and the random forest. Okay, so that's what we have done for the slurry pipelines. This is a work which is currently under study. We are using more data, and as I said, the objective for us is instead, because we spend many time or many work trying to fix the data and get the empirical equation. That's what we call the constitutive model. So now we are trying to convince logically that forget that won't work, because we are only going to fix that data with a nonlinear equation because there is other parameters that should be possible. Now we are trying to convince them, instead of doing that work, you can use this data, the data you have from the beginning when you build the pipe until now, which is 2012 to this time of the year, which is a new set of data, teach your machine with that data, and then do the modelization based on what the machine gives you. So that's exactly where we're going. We are not convinced yet, but that's exactly what we are trying to do. And then the problem is, the model will be always relying on the data, because people who did the modelization before, when we build a model, they not disconnected with data. So you build a model to generate the data, not data for modeling. So that's something that the concept is not working yet, but that's exactly what we're doing. So we're trying to build a model where anytime it's a viscosity of the phosphate, go back to the set of data, ask the machine which has been trained to give you the right equation or right formula, and then carry on. Then, at a given time, we need that constitutive model, use the data. That's what it's going to do. Okay. I hope you have understand the concept. Now, I will talk about something we have done quickly on the sediment transport. So we did something we have been working on sediment transport for 10 years or more, and we have done some work for the lagoon of Nado, and we tried also to use some machine learning for sediment transport, and I will tell you why. And again, this is something we are still interested to do collaboration. So that's, I think people from hydraulics, they left, so they should know this. So that's a domain, so where we have water, and then you have sediments. So when you do sediment transport, you have suspended sediment, those particles on the water, and then you have a bed, which we call the bathymetry, and we try to understand how the bathymetry is moving. They have this problem also in Mehdia, because they get sand, they get a lot of erosion, and then you have some beaches that just disappear. So that's exactly what we want to do in the novel. So we are not going to solve the 3D model because the surface of the water is moving. You need to remesh every time. We don't do modeling with this one, but we integrate and we try to understand very simply simplified model. So what we end up with, moving from 3D to 2D. Okay. Equations are terrible. So for those who never did PDEs, this is Chinese. Okay, but forget it. But the problem is, what I want to emphasize here, there is a lot of parameters. Very hard to identify them. We don't have a formula that tells you, if you are dealing with the clay, this is what you use. If you are dealing with the sand, this is what you use. If you are dealing with different materials, that's what you use. It's nothing like that. There's a lot of dependency on those parameters. You have density, porosity, erosion, deposition, coriolis, stress. It's all the diseases you have learned in PDEs are here. Okay? And at the, at the end, it's hyperbolic. So people that have used PDEs, it's very hard to solve this. To solve it from a numerical point of view, and also from a quantitative analysis or sensitivity analysis for those parameters. Because if you have a client, you want to sell this for me, first thing I will ask you, how your model, depending on those parameters, is it robust? If I change low, would this be stable? If I change porosity, if I establish. So that's the kind of problems where machine learning can answer those questions. Okay. So, as I said, I can show you how these problems are very difficult. So you have discrepancy on the time scale because you have water moving with the speed of the sound, and then you have the bathymetry moving with a different speed. You have two scales all the time, and also you have different, very complex angle values for this system, and something really not easy to solve. Okay. So, and then you see here, if you do some asymptotic analysis, you want to understand how the water, H is just the water height, U is the velocity, and then you have some fluid number, some bathymetry, and then some concentration of those particles moving on the bed. We know how to do this. These are our work, you know. So that's something we have been doing for, as I said, 10 years. But the thing we don't know is the parameters involved, especially when you have erosion deposition. Those are data. So there's no equations for these terms. Okay. So then what we want to do, I will show you how we do forward problem, and then where machine learning can be used here. If you have been in Nado, so this is the lagoon of Nado, Marchiga. Okay. So Marchiga, that's something we have been working. We have, I think, 3 PhD students released their thesis just here. So this is a lagoon which has only one bypass here, when the water from the Mediterranean goes to the lagoon. There's a lot of fishery here, a lot of industry as well, and here a lot of hotels, and a lot of infrastructure there. The problem with Israel, because of the sediment transport, you have some dead area. Okay, because of the sediment, they come down and then it stays, becomes smelly, and there is no what we call electrification. Okay, what they want to do recently, they want to open 2 bypass. One for the water to come from the Mediterranean, and then it takes longer, and then it go out, because that recirculation is not complete. Okay, so we work on this project. We have a lot of data, of course, and most of the data coming from people doing biology, because they have a lot of observatories here. We have all the data. Anything of data you think of, we have in this lab in Marchina. And the idea was, especially in our case, to try to find where the best place to put another bypass. Because that moving, that's something we need some understanding of the flow and also the behavior of the sediment. Should be here, should be there, should be there, or should be somewhere else. Now they have put 2 bypass. If you have been there, so they put one here and they put a dam or a port to make sure that they have a lot of trouble as well. Okay. In our case, we want to understand how the sediment will move and where it should be going. We do finite element, we call it, that's something we know that don't worry about it. So that's very easy. You see the sediment coming from the Mediterranean and just how it moves. You see the cell, it goes there. So this is a high sedimentation. That means that area will be most affected with the sand coming from the Mediterranean. That's something I can also show you if this works. I don't know why it doesn't work. So that's, yeah, so that's the tide, because the water coming from there is a tide, 24 hours every day, and it takes 6 hours to come, and then it goes out. You see this area which will be most affected. All the sediment will be here, a deposition. This is what we call the dead zone. Because what we did in one of the PhD, we're trying to see what we call the residence time. The residence time, if a particle of water enters, how long it takes to go out. Okay, so we can do that. We have tools to do. Is this another movie? Yeah, so this is exactly the same again. So you see the time, so you see the sediment is just going there, and then it starts to circulate, and that's some area will be most affected. Okay, but again, here we have done some assumptions. We have assumed the world is fine, which are wrong, because we couldn't compare to the experiment data. Now, we have data, we have access to data. Why don't we use machine learning and then solve these problems, especially when we have a lot of parameters? But the difference between this problem and the problem I showed you at the beginning, which is the slurry pipelines, this one is a decision, okay, rather than estimation. Because the first one I showed you, how can we use machine learning to estimate viscosity or elasticity? But here, no, it's just to make the decision which equation to use. We have more than 1,500 equations for this erosion deposition, but which one to use? It depends on the flow velocities, the type of the sediment, the saturation of the soil. There's a lot of dependency there. Now, can we use the machine learning to tell us or to decide which equation to use for A, which equation to use for D, which equation to use for other parameters? And again, we have those parameters which really affect how the sediment will be transported. Again, this is just as I showed you before, this is around the forest, and then you sample your data, you use some data for training your machine, and then some data to evaluate the model. There's a lot of set of data. It's a big data if you want. I don't know how you explain big data, but it's really not homogeneous. It's not scalable. depends of course of the machine, but it's a really huge set of data which we have to run in big machines. And then you sample those data in different layers. Some of them you put the parameters where you might think they are very relevant for the problem, and then as long as you go farther from those layers, you put the ones you don't care. That's again a random forest tree, and then you make the decision just by yes or no. Once you train your machine, you can have that decision by default. Again, if we're going to sell this to a client, you won't be interested to understand how it's done. For him, switch on, switch off. It's as a machine, as a black box here. But for us, and especially for people sitting in this room, they want to understand what's going on in that black box, and can we speed it? Can we make it more optimized, more robust? And that's where the research will be very interesting. That's a debris we will put in the lab. So you see the erosion thing there. Depend on this is a multi-layer where you have a soil with sand, clay, and then some rock there. And this experiment my student they run in the lab to get data. So we can, what I will show you, we have two types of data. So we have data from the field, where people, they go to the field, engineering technicians, they get data. Or people, they can run this on the lab and then get the data. Again, if I show you what we get from the lab, this is the data from the lab, this is data from the field which we have access to, and now you have the errors for the velocity of the flow and then the diameter of the sediment, because we need to, the equations for E and D depend on the size of the diameter of those particles of the sediment. And as you see again, this is a heterogeneous data, and we will have very high errors for some given velocity and diameter. So when we teach our machine, we keep one parameter fixed, and then we change the input-output. Fix one, and then see what happened to the others. Okay, and here where you see the predicted and the data, this is the velocity of the flow, concentration of the sediment, and the water height, and then you see very nice matching. This is mainly done by machine learning. Okay, if you look at the errors, again, so the errors between I think this is the concentration, and this is the diameter. This is the velocity of the flow, and you see you have almost most of the data, or most of the results, the errors are very, very small. And these are mainly coming from random forest of decision based on machine learning. Okay, and again, this is something we do for to see whether we mix where are the places we can mix the experimental data and where we have the errors, and you see somewhat still has to be done here, but in these areas we can really capture the sediment transport just using the machine learning. If we compare the experimental data, this is a work done on the lab. You see those cross, those are measurements from the lab. That's the water surface. You see a hydraulic jump here, and then you have the erosion on the bed. Initially it was flat, and you see that's machine learning for the bed, and that's the machine learning for age. And then you have some data which has been carried on at Delft University. They do these type of problems, and we can see that machine learning, this is pure machine learning. We don't run nothing. We don't do any fundamental or nothing. Just decision based on, we teach the machine, and then we run the simulation, asking the machine learning to tell us what is the water height and what is the bed. Okay. Good. I should stop here and just tell you where we are. That's the truth. We believe, like you guys, even I'm applied mathematician. So we believe that machine learning is very, very useful nowadays to solve many problems. Because, especially when we go to conferences, we have this
conflict or fighting. There's people they do modelization and some people they do data analysis and they start to fight. I don't have religion on that, so for me, so I say modeling is the thing you should do. The other guys they say, no, why are you doing modeling? We can do data analysis because this is true. We have access to data, and especially in this time, because you can collect data very easy, cheap. The Chinese, they put sensors with £1 or maybe $1. Yeah. And then you can collect data, as many data you want. But is data enough to understand the whole physics and to make the decision? That's something that needs to be questioned. Yes, I believe that machine learning can be very good to solve problems. Like the name as well, so it is really, especially for engineering, is a sustainable tools to answer many questions. And this is why basically now we have putting a lot of money on data analysis, artificial intelligence, machine learning, deep learning, all these kind of stuff. So now, because from the beginning up to this stage, they have collected a lot of data. I'm talking about mega or giga data. And then they want to use that data maybe for some purposes. Okay, now, what is the challenge? We need multidisciplinary. Okay, if you guys from this intelligence, artificial, you sit in the room, close the door, and you try to progress, you won't do it, believe me. So we need this multidisciplinary or interdisciplinary. So you need physics to talk to informatics or computer science, the biologist, the chemist, the math, all these interdisciplinary improve these kind of things. If you believe that you can do lots of things just for your own, that's wrong. You are mistake. You don't do mistake. So this thing can be helping a lot. And this is why they asked me to come to do this presentation. I didn't hesitate because I'm learning from you. You know better this stuff than me, which is not my area of research. Okay, so that's something really we need. We need that to understand each other. Because I'm speaking better, these guys speaking Arabic, these guys speaking. In terms of research, we're talking. We need to understand each other. Now, that's two still open questions. Are we solving the right equation? I don't know. I shall do those equations, but who tells us the right is the best thing to do? There is other stuff to do. But this is still an open question. The other thing is, نقلب سؤال واش كان solving the equation right? واش those tools we are using is random forest the best? Is the neural network the best? Oh, there is other stuff there. So these are still open questions. We can do a lot of research. Thank you very much.
Merci Mohamed pour cette conférence fort intéressante. Est-ce qu'il y a des questions? Je ne vais pas. C'est monsieur.
Concernant le processus de vérification, je pense que l'utilisation des systèmes logiques, ça donne la piste de résultat parce que vous pouvez suivre le raisonnement du système, c'est-à-dire le raisonnement des machines. Par contre, les systèmes d'apprentissage, vous ne pouvez pas suivre, vous pouvez seulement observer ce qui se passe dedans, mais vous ne pouvez pas tracer le raisonnement du système. Comme ça, vous pouvez vérifier le système c'est correct, il est fait, la solution est correcte ou la solution cherchée est correcte.
Et aujourd'hui, c'est faire la concision ou faire juste la décision avec le raisonnement.
C'est-à-dire comment on vérifie que la solution est correcte, les équations que vous cherchez à résoudre.
Parce que ce qu'on fait, c'est juste de prendre des data, ensemble, 10%, 10%, pour vérifier si la machine nous donne quelque chose.
Donc vous faites les deux systèmes, le système logique et le système d'apprentissage, pour comparer entre les deux.
Bien sûr.
Merci.
Pour le problème sur plusieurs éléments, il y a deux choses. Il y a la décision entre l'équation et le choix de paramètres. Et نحتاج l'équation qui a des paramètres hyper paramètres, les choisir. Comment on va le choisir? C'est on fait la décision de choisir quelle équation pour l'érosion de position, et après, quel est le choix? Il y a des paramètres les forts.
Juste une petite remarque par rapport à la première équation à Stokes que Mohamed nous a exposée. Donc d'abord, le choix de la modélisation, c'est de dire, tiens, on va considérer le problème de Navier-Stokes avec un tenseur de viscosité. Ça, c'est le premier choix. Donc, c'est une décision à prendre. Une fois après la décision, donc, il y a un problème de voie de comportement. Comment on va choisir le courant taux là, égal à quoi en fonction de la vitesse. Donc, il y avait 3 modèles qui ont été choisis. D'accord? Ces modèles-là, ils contiennent des paramètres. Donc, il a considéré un problème inverse. Qu'est-ce que c'est qu'un problème inverse? Étant donné quelques mesures sur la solution qui est la vitesse, peut-on remonter aux coefficients qui sont intrinsèques à notre modèle mathématique? Et là, il y a beaucoup d'études qui ont été faites. Donc, au départ, c'était avec l'IIMSC, des jalons, etc. Donc, on utilise des techniques de contrôle optimal. Et à la fin des années 2000, donc, est arrivé les algorithmes génétiques, et maintenant, donc, ça donne de très bons résultats d'ailleurs des algorithmes génétiques. Et c'est Mohamed maintenant, elle nous ramène vers l'utilisation des machine learning pour identifier 2 coefficients qui sont le coefficient de l'élasticité et le coefficient de la viscoélasticité. Et c'est un problème très difficile. Mathématiquement, c'est un problème mal posé. Il se peut qu'il y ait plusieurs solutions. Donc il faut ajouter des contraintes pour pouvoir sélectionner la bonne solution qui est physique et qui est adaptée aux données. C'est pour cela que la machine learning, avec beaucoup de données, on pourra cerner le problème et donner exactement les vrais paramètres. En fait, pour les problèmes inverses, c'est une solution miraculeuse parce que identifier les paramètres, pour les inverses classiquement, on prend des données, un échantillon de données, et on essaie d'identifier. Ce n'est pas suffisant. Machine learning, on utilise beaucoup de données, une base de données qui est très grande. Et donc, on arrive donc à faire l'apprentissage et à déduire les paramètres qui ne vérifient aucune équation d'ailleurs. C'est ça le problème, parce que les paramètres dans les équations ou les règles partielles ne vérifient aucune équation. C'est pour ça qu'on ne peut pas les trouver directement. Le deuxième problème que M. Mohamed a exposé, c'est un problème aussi très difficile. Le premier, il est parabolique, non linéaire. Et le second, il est hyperbolique. Même en dimension 1, ça pose des questions mathématiques très sévères. Ça pose un problème très difficile. Bien sûr, il est régularisé, parce qu'on voit qu'il y a une virgule seconde au second membre. Mais il a posé une question plus difficile que celle-là. Il cherche les paramètres. Et on sait déjà que pour les problèmes linéaires, il y a un problème. Le problème de transport, c'est un problème de transport à les équations hyperboliques de premier ordre, ça modélise bien le transport. Déjà, ils sont non linéaires. Déjà, le problème direct, il est mal posé. Et le problème d'optimisation aussi. Et donc, la solution reste, je crois, qui est portée par les données et machine learning directement, sans vraiment passer par les mathématiques, parce que les modèles sont mal posés. Donc, si je peux résumer l'intervention de Simon. Donc, c'est là. Alors, est-ce qu'il y a d'autres questions? Bien sûr, d'ailleurs, dans le transparent, je vois que c'est un carrefour de connaissances. C'est-à-dire que multidisciplinaire, il y a la modélisation, il y a la physique, il y a les mathématiques, il y a de l'informatique. Déjà, si on parle ici que le schéma numérique, est-ce qu'il converge oui ou non? Est-ce que le problème mathématique est bien posé oui ou non? Chaque question, c'est une discipline à part. Et ce problème-là a été traité par plusieurs personnes. D'ailleurs, il y a un prix proposé par les États-Unis, $1 million pour résoudre ces équations-là. C'est pas facile. Déjà, le problème direct est difficile. Par contre, le problème inverse, c'est encore plus difficile. Par contre, l'espoir, c'est dans les machines learning. Peut-être que ça va nous guider vers la vraie solution.
Merci pour cette présentation. Moi, je ne vais pas discuter les paramètres relatifs à l'équation de la phosphate. Donc, pour acheminer le phosphate, donc, il faut le mélanger à deux. Est-ce qu'il n'y a pas d'autre solution beaucoup plus optimale que celle de transport des phosphates à l'aide de l'eau? Et comme ça, on peut éviter donc, la discussion de ces paramètres.
Exactement. D'abord, le processus il doit être visqueux. Sinon, même si je ne veux pas.
L'air, compression à l'aide de l'air, par exemple.
Non,
La même chose.
Pour un long terme, c'est un fluide compressé. Ce qu'on fait, c'est des fluides incompressibles. L'air, c'est compressé. C'est des matériaux qui ne sont pas l'épaisseur de l'air, c'est juste pour la croissance. Non, les chimistes, là, c'est parce qu'il y a des chimistes qui ont des additifs. Des additifs chimiques باش يلعبوا في لا فيسكوسيتي ديال الفوسفات ويأكسيليرو لو بروسيس. من الماء ما عندك منه هروب، سي توجور تدوز جوان في عندك ليكيد، سينو ما ترونسبورتاش. دابا المشكل شكون نعملو؟ كنجيبوه من لامين كيكون سيش، كيكون غلاظ. كنمشيو نخلطوه في الدار ونعملوه ونمشيوه في البايب ملي كيمشي الجوف راه كنشفوه. هما كيف يعني ما عندناش شي واحد الموسيقى. هو سينا جاوب. ياك فكاينه بروبليم مي او نيفو ديال يعني سي انكرويابل. برودكسيون باش لا برودكسيون باش تاخذ داكشي بالتران راه مصيبه. فقط دابا لا برودكسيون ما كتوقفش راه 24 hours و 365 دايف لا كعفو لا عيد لا موسم لا 24 والنهار